Hello, this lecture is just going to be a review of topics that we have covered that were not on the first quiz. So first off, rotation. Main thing to remind you of with this is that we learned rotational variables, but they have linear counterparts. So we have position in X or Y, and we have angular position, which is given by theta. We have velocity and we have angular velocity, which is just like velocity is the displacement over the time interval. Angular velocity is angular displacement over the, and then we have angular acceleration, which is the change in angular velocity over the time interval. These two equations are just rearranging these ones. And then we also have an angular version of the long kinematics equation. So this is the long kinematics equation, except for usually we break up the displacement into initial and final position. So linear motion and circular motion are very similar to each other. Then we talked about centripetal acceleration or center seeking. So when an object is moving in a circle, in order for it to continue to move in the circle, it needs to experience acceleration pointing toward the center of the circle. That acceleration changes the direction of the velocity, which is what causes circular motion. And the relationship between centripetal acceleration and the velocity of circular motion can be derived into this equation where centripetal acceleration is the velocity squared divided by the radius of the circular motion. And if there is an acceleration, there must be a net force in that same direction. So we also have the centripetal force too, you can think of, or it's really just the net force caused by some combination of forces, but it needs to be always pointing toward the center of the circle if it's in circular motion. And because this net force is mass times the centripetal acceleration, we can also plug in v squared over r into the force equation too. We have angular velocity and velocity from kind of different sources. So here the T is not tension, it is period, which is just the time it takes to make one complete orbit or circle or what have you. And both of these, so this one, 2 pi radians is the angle of a complete circle. And then 2 pi r is the distance, kind of the perimeter of a complete circle. So we have the angular displacement divided by the time interval, and we have the displacement divided by the time interval. So just showing different ways we can get these velocities, and then we can relate them to each other. So the linear velocity is the angular velocity times the radius. And this, remember, works when the angular velocity is in radians per second, because we talked about radians aren't actually a real unit. And this radius would be in meters, giving us velocity in meters per second. Okay. Then related to this is some orbital motion stuff. Specifically free fall, where the only force experienced is the weight force. So we can look at what that looks like using our centripetal acceleration. And this, because we're talking about orbital motion here, this becomes the orbital velocity. So the orbital velocity is the square root of free fall acceleration or acceleration due to gravity times the radius. And this is also the critical velocity for circular motion. So in order for an object to complete circular motion, it must have a velocity of at least the square root of angular acceleration times the radius of the circle. Then we also talked about the concept of apparent weight. So this works in circular motion, but also works just in situations where there's some acceleration, like we have an elevator that's moving up and accelerating. So we're looking at the free body diagram of a person in the elevator, their normal force and their weight force, and we know the net force is up, so the normal force needs to be bigger than the weight force. And we can, from our free body diagram, get our net force equation, rearrange it, and solve for the normal force, and we get this. We get that the normal force in this situation is equal to the weight plus the mass times whatever the acceleration is. And this is, this normal force here is the apparent weight. And in general, the apparent weight is just the magnitude of supporting contact forces. So it's the weight you feel. When it comes to accelerated motion like this, the direction of the acceleration affects the apparent weight you experience. When it comes to circular motion, even if you can't always necessarily feel the acceleration, you know that in circular motion, there's acceleration toward the center of the circle. So there is a net force, and that's going to contribute to the apparent weight you feel. And so to solve problems like this, you need to draw the free body diagram, thing one, including the direction of the net force. And then you need to write the force equations. And I don't mean just skipping to this step. I really should have this slide, but I mean writing net force equals mass times acceleration equals the sum of forces that are acting, and then solve for the normal force from that, because you can't always easily intuit whether or not the apparent weight is greater than, less than, or equal to the true weight. So it's important to start from a baseline, and that is your free body diagram and force equation. Next step, gravity. The orbit thing definitely could have tied in with gravity, but specifically gravity is Newton's law of gravitation. So we have two planets here, or honestly, any two massive objects. Their distance are apart. Each one has its own mass, and they have a gravitational, or they each have a gravitational force that acts on the other. And that force is given by this capital G, which is the universal gravitation constant, or constant of universal gravitation, I think is the order. And it's this here at 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. So the force is that G times the mass of each of the gravitational bodies divided by the distance between them squared. And these forces, so mass 1 experiences this force from mass 2, and mass 2 experiences this force from mass 1. But you can see, for one thing, from the equation, the magnitude is going to be the same because both masses are in there and the distance is the same. So, but this is also an action-reaction pair of forces too. Not only can you see it from the equation, also already an action-reaction pair, but these are not contact forces. They don't need to touch each other to impart forces on each other. Okay, and then I also want to talk about local free fall acceleration or acceleration due to gravity on other planets. If you look back at the lectures on this, we derived this equation, but the equation we get for this is the free fall acceleration of the planet is that G, again, that constant, times the mass of the planet divided by the radius of the planet squared. So you have the mass of a planet and the radius of it, you can figure out what the free fall acceleration would be. Okay, now work and energy. So work is a transfer of energy into or out of a system through a force applied over a certain distance. And the part of the force that we care about is the part that is in parallel with direction with the motion. So we have this situation, but in like kind of free body diagram form, sort of, except for just looking at this one tension force. The motion is going to be horizontal. The force acts at an angle, but the portion of the force that we care about with respect to work done is this parallel component. And I want to note also, this works for parallel or anti-parallel. So parallel being in the same direction, anti-parallel being in opposite directions. It just changes the sign, is all. So anyway, work is the parallel component of the force times the distance traveled, which usually is going to end up being FD cosine theta, where theta is the angle between the direction of the force and the displacement. Kinetic energy can also change when work is done on a system. So in this case, there was a force pulling on this car. It started with an initial velocity. The force pulls over a distance, and then we have a larger final velocity. So the work done is the change in kinetic energy. And kinetic energy is 1/2 the mass times the velocity squared. We also talked about gravitational potential energy and how moving an object to a different height or like a different vertical position also changes the potential energy, gravitational potential energy of the system. And there's kind of these two ways we can look at it. It can either be the change in gravitational potential energy, which is the mass times the free fall acceleration times the change in height, or if you're just looking for the gravitational potential energy at a specific point, it's the mass times free fall acceleration times whatever that height is. We also talked about conservation of energy, which is where in an isolated system, only conservative forces are acting, which gravitational potential energy, or sorry, gravitational force is a conservative force. But in situations like that, the mechanical energy is constant. Mechanical energy is given by this capital E, and it's just the kinetic plus the potential. And if it's constant, it means that the initial mechanical energy is equal to the final mechanical energy, or the main thing we've used is that the initial kinetic plus initial potential equals the final kinetic plus final potential. And you can use that to see things like if we have an initial velocity, how high up an incline can an object get just via conservation of energy? Or if we start up this high, what would our velocity be at the ground only based on conservation of energy? And then the most recent stuff we've talked about is impulse and momentum. There is the impulse momentum theorem, where an impulse is delivered to an object and that causes the object's momentum to change. So momentum is not on this slide, but it's mass times velocity. And impulse is either the change in momentum or the average force experienced for over a time interval. And we have different types of collisions with this. And we talked about how for these collisions, we end up with conservation of momentum, where the total initial momentum of a system is equal to the total final momentum. So we have these two balls that collide. They are in collision for a certain time and experience an impulse through that. And then after they have, each object has a different velocity, but the momentum of the system is the same. So there's elastic collisions where the objects collide and then bounce apart. There's inelastic collisions where the objects collide and then stick together. So for example, in this one has a bigger mass and a bigger velocity. So we can see that what happens is they end up moving in the direction of this one. And you could figure out here what the initial momentum of the system is, and then that would tell you what the final momentum of the system should be. And then finally, there's explosions, which are not necessarily always explosive, but it is when the objects start together and then break apart in some form. From the activity, in-class activity on Tuesday, the example of the two figure skaters pushing off of each other, that was an explosion. Because they started together, they weren't moving in their case, which objects can be moving initially. And then they pushed off of each other. And from that, we know that their initial momentum was 0, which means their final momentum needed to be 0. So they should have equal and opposite momentum. Anyway, so that's an explosion. Like I said, doesn't have to be explosive. And if you want to look at the conservation of momentum equations for these different collisions, you can look in the notes, or I guess it's the lecture examples from Tuesday. Okay, so after this, you're gonna have a post-lecture activity to work on, and then we are going to practice some more of these topics on Thursday as well. Have a great day.